This is a molecule, of paracetamol to be precise, and these are two polymorphs of the paracetamol crystal. They are molecular crystals, which means they are composed of molecular blocks, the arrangement of which determines some of their properties. Characterizing such systems is often a hard task due to their almost degeneracy in energy, and spectroscopic techniques like Raman are useful in that regard. Indeed, such systems typically have very specific fingerprints in vibrational spectra, allowing one to distinguish between different polymorphs. To simulate vibrational Raman spectra, one way is to run a molecular dynamics trajectory, on top of which one computes polarizability tensors. Each component experiences periodic variations over time, which are then used to compute the Raman spectrum through an autocorrelation function formalism. Such calculations are typically very expensive, as tens of thousands of polarizability calculations need to be carried out. Furthermore, such samplings contain a lot of similar-looking structures. Suppose we know, say, the polarizabilities of two different structures, and would like to interpolate the polarizability of a third configuration without resorting to any ab initio calculation. To achieve this, we use in this work Gaussian process regression approaches, a type of supervised machine learning, offering us a way to navigate through all the configuration space and learn the mapping between a geometrical configuration and its corresponding polarizability tensor. Any model based on a Gaussian process regression, or GPR in short, depends on hyperparameters that need to be adjusted so as to get some flexibility to the predictions. Increasing the number of training points increases the accuracy of our results, but the amount of training points needed will highly depend on the complexity of the system. Our approach works both for molecules and solids. However, in the particular case of molecular crystals, more information can be gathered and fed to the algorithm. Indeed, the polarizability tensors of each of the individual molecules constituting the crystal can be easily obtained. We can then sum them up and use them as a baseline for GPR, reducing the amount of training points necessary. Finally, instead of having to retrain our models each time a new polymer is encountered, we exploit the similarity of the atomic environments in this kind of crystals. By using a symmetry-adapted GPR with lambda soap kernels, based on the smooth overlap of atomic positions, we're able to extrapolate the polarizability of a given polymorph based on the sole knowledge of another polymorph, and also get confidence intervals on our predictions, hence demonstrating the transferability of this model. For details, please have a look at our article.